Welcome back. This is Jennifer Dassinger with A Plus College Ready, and I'm back with you with bonding and molecular geometry, drawing Lewis structures. So let's review our notes again. Go back to the last video if you need to, but we're now going to dive into some examples of how to draw Lewis structures. So our first one is nitrogen trifluoride, NF3. How did I draw the structure? Well, obviously animate the structure at the bottom. Well, first, step one, nitrogen, the least electronegative element, then fluorine. So nitrogen has to be the center atom. Step two, count the valence electrons. Nitrogen has 5, fluorine has 7. Remember, due to your electron configuration of those valence electrons. So 5 plus 3 times 7, because there's 3 atoms of your valence electrons of fluorine, you'll have a total of 26 valence electrons. Step 3, draw single bonds between the nitrogen and fluorine atoms. Complete octet on sodium and fluorine atoms. So notice, count them up. Do I have 8 around each? Check. Are the number of electrons in the structure equal to the number of valence electrons? 3 single bonds, 3 times 2, plus the 10 lone pairs, or unshared pairs, remember, 10 times 2, 26 valence electrons. Let's look at another example. Here's a skeletal structure of formaldehyde, CH2O. Now, there could be another format for this. Let's go through this. This is what's called formal charge, and the equation is down at the bottom. Formal charge is equal to the total number of valence electrons in the free atom minus the total number of non-bonded electrons minus 1/2 the total number of bonded electrons. Well, let's look at that. That's the definition of formal charge. It's the difference between the number of valence electrons in an isolated atom and the number of electrons assigned to that atom. And that's the sum. Here's the crucial part. If it is a molecule, that sum must equal 0. If it is an ion, such as ammonium, it should be a positive, equal to a positive 1. If it's another polyatomic ion, such as nitrate, NO3 negative 1, it must equal to negative 1. Let's go through the rest of our example. Here's another structural format of our formaldehyde. Notice I've taken my valence electrons, put my single bonds and my double bonds in, and I have a total of 12 electrons. Now to calculate the formal charge to see if I have a correct answer. So I should equal to 0. So I take my 4 minus 2. Remember, total number of valence electrons is 4, minus the total number of my non-bonded, which is 2 on carbon, minus my 1/2 times 6, remember 6 for my oxygen, is equal to negative 1. Well, this can't be correct because I needed a formal charge of 0 on carbon and 0 on oxygen. So if you calculate that for carbon and calculate it for oxygen, I will have a +1 for oxygen and a -1 for carbon. So let's look at the other example that I had previously with its formal charge. I have my total valence electrons calculated. I'm plugging into my equation. For carbon, 4 minus 0, 1/2 times 8, 0. On my oxygen, 6 minus my 4 of unbonded minus 1/2 times my 4 total number of bonded will equal 0. So therefore, this is the best structure based upon its formal charge. 0 and 0. Again, Neutral molecules' Lewis structure in which there's no formal charge is preferable to the one with formal charges present. So that's why the formaldehyde structure on the left was not the correct one, because it had a -1 and a +1 on the carbon and oxygen. The formal charge on the right made sure that I had a 0 and a 0. That's why it's the correct Lewis structure. Let's look at some more. Resonance structures is where you have 2 or more Lewis structures that can represent the possible structure. So for ozone, for example, you're going to have a blended structure. The formal charge is actually going to be our bond order is not going to be a whole number. It's going to be a half of a number, like a 1.5 or 2.5. So in resonance, the double bond essentially can flip from one side to another. For example, carbonate has a resonance structure. Notice it has 3 possible sites of the double bond. And again, that goes back to its formal charge that we just looked at before. So when you calculate the formal charge and you see, wait a minute, there's more than one possible resolution, you know you're in the land of resonance. And yes, on the AP exam, you must draw all possible structures that have resonance. So if you have a carbonate, you have a sulfur trioxide, you're gonna have to draw all 3. I'm sorry, but that is what it is. Notice some exceptions to the octet rule. We talked about hydrogen earlier in terms of being a terminal atom and only having 2 electrons. Well, beryllium and boron are also exceptions to the octet rule. Notice beryllium only has 2 valence electrons. Boron has 3. So it will only attain, no more on beryllium, only attain 2. And boron will only attain, 4 total. And then boron will maximize at 6 total, not 8. All right, so let's look at our bond energy. Remember, we're always looking at the lowest possible energy when creating a molecule. And remember, it takes more energy to break a bond than make a bond. So if you look at the bond energy values that are given in this table, and if you notice in terms of a single, a double, and a triple bond, remember earlier we were looking at that a triple bond has a smaller value in terms of the radius than the single bond? Well, now that you look at the bond energy, you can also see that a triple bond has a greater bond energy than a single bond because it takes more energy to break those triple bonds than it does that single bond, and also a double. So how do we calculate bond energy? Well, bond energy, affectionately known as the backwards equation to Hess, is where we take the bonds broken, aka reactants, minus bonds formed, aka products. So again, total energy taken in minus the total energy being released. Or as we like to say, reactants, the sum of the reactants minus the sum of the products. So let's take some examples. On the AP exam, you're going to be given a balanced equation, or maybe you have to balance the equation. Don't forget, sum means including the moles. So if you look at how we make hydrofluoric acid, notice hydrogen to hydrogen is a reactant. It has 1 bond being broken, it has 1 bond energy. Fluorine to fluorine has 1 mole, 1 bond being broken. However, hydrofluoric acid, there are 2 moles, so number of 2 bonds formed, and it has a bond energy for single. So therefore, by plugging into our equation, we take the sum of our reactants, the hydrogen to hydrogen and the fluorine to fluorine, minus 2 times, that's the number of moles, times our bond energy for hydrofluoric acid, and we will achieve a negative 543.1 kilojoules per mole of energy. That's a lot of energy. So, final check. Draw a Lewis structure of sulfur dioxide, calculate the formal charge, and make sure you draw all possible shapes of your sulfur dioxide. Keep practicing. Your teacher will have more practice for you, and we'll be reviewing some of these concepts in our concept checks and in our practice problems. Good luck, and draw the Lewis structure.